Is that working? Okay. So it's an interesting time in computing. You've got the confluence of Moore's law and Dennard scaling being completely dead, with AI just scaling like crazy. You have a pretty unique position in the world of driving these supercomputers and the infrastructure that is being built. And you know, like how to map the workloads onto these things, which is a unique sort of skill. What do you think the future of computing is going to look like? What is the computing infrastructure heading towards, like from an asymptotic thought experiment level?
Yeah, I mean, it's really clear that we will have dramatically changed the kinds of computations we want to run on computers in the last, say, 5 years, 10 years. And that was like initially a small ripple, but it's pretty clear now that you want to run incredibly large neural networks at incredibly high performance and incredibly low power. And you also want to train them. Training and inference are pretty different kinds of workloads. So I think it's useful to think of those two as, you know, you probably want different solutions for the two, or somewhat specialized solutions. And I think you're going to see all kinds of adaptation of compute platforms for this new reality that you really just want to run incredibly capable models. And so some of that will be in low power environments like your phone. Like you'd like your phone to run incredibly good models with lots of parameters super fast, so that when you talk to your phone, it just talks back to you and it can help you do all kinds of things. You're going to want to run these on robots and autonomous vehicles. You know, we already do somewhat, but even better hardware for that will make those systems much easier to build, much more capable, you know, physical agents in the world. And then you want to run them at incredibly large scale in data centers. And then you also then want to use lots of inference time compute for some kinds of problems, but not others. So you have you know, it's pretty clear you want to use 10,000 times as much compute for some problems as for others. And that's a nice new scaling knob we have that can make your model much more capable or give you, you know, much better answers or make the model capable of doing things with that much compute that it can't do with you know, 1x as much compute. But you shouldn't spend 10,000 times as much compute on everything. So how do you make your systems work well for that? And I think that's a combination of hardware, system software, you know, model and algorithmic tricks, distillation, all these things can help you make amazing models come to life in small compute footprints.
One thing I've noticed is the computer science, at least traditionally, you know, when people are studying algorithms and computational complexity, it was all op count based. And I think as people are rediscovering hardware and details of hardware and system design, I think one of the things that's come back into focus is you need to think about network bandwidth and memory bandwidth and so forth. And so I think a lot of the kind of traditional algorithmic analysis needs to be completely rethought, just because of realities of what real computation looks like.
Yeah, one of my office mates in grad school did his thesis on like cache aware algorithms because the order of magnitude big O kind of notation didn't account for the fact that some operations are 100x worse than others.
Yeah, no, that's right.
And I think in modern ML computing, you care about data movement at the incredibly small level, like moving things from SRAM into accumulators costs you some tiny number of picojoules, but it's way more than the actual operation costs you. So it's important to have picojoules at the tip of your tongue these days.
One other